Namaskar and welcome to this channel. Today we are going to discuss about 1 ampere current, how 1 ampere current is defined and some important points related to 1 ampere current, and also the types of electric current. There are basically two types of current. The first one is DC current and last one is AC current. And then we discuss about the particles involved in electrical conduction in some materials and mechanism of metallic conductions, how a metal can conduct electricity, what is the mechanism of electrical conduction inside the metal. So we will discuss it later. And last but not the least, the drift velocity. We will define drift velocity and its famous expression, which is also important for NAB board exam. Please, you can think this as a regular class and you can make a note by writing down what you have seen here. You can make a separate note for current, electricity. This is our DC circuits lecture 2. Now let's get started. First of all, we understand the 1 ampere current. We have a simple expression for electric current is I equals Q by T. Here Q means charge and T means time. So current is the time rate of flow of charge. If we put charge Q as 1 coulomb and time T is 1 second, then we finally get current as 1 ampere. This is the mathematical relations. So these mathematical relations can be expressed in language form as the 1 ampere current is simply a flow of 1 coulomb charge in 1 second in a definite direction through any cross section of a conductor. Here the definite direction means in a particular direction. Current always flow in a particular direction. For example, in a battery, the current always flow from positive terminal of a battery to the negative terminal of a battery. So this direction of flow of current is a definite direction that you can suppose. So simply 1 ampere current means flow of 1 coulomb charge in 1 second in a definite direction through any cross section of a conductor. This definition of 1 ampere current is important because it is frequently asked in our board exam. Now here are some notes, that means some key points related to 1 ampere current. We know that 1.6 into 10 to the power minus 19 coulomb equals 1 electrons. From unitary method, 1 coulomb consists of 6.25 into 10 to the power 18 electrons. This is important. If someone asks you how many electrons consist of in 1 coulomb charge, then at that time you must say in 1 coulomb charge there exists of 6.25 into 10 to the power 18 electrons. I hope you understand, and please remember this one. Remember, 1 ampere current means 1 coulomb charge in 1 second. This is the definition. So finally we get 6.25 into 10 to the power 18 electrons in 1 second. So 1 ampere current simply means a flow of 6.25 into 10 to the power 18 electrons in 1 second. Please remember this value. Alright, I hope you understand this slide. Let's move on to next. This is my Facebook page. Now let's talk about the types of electric current. Basically there are two types of electric current. The first one is DC and next one is AC. DC means direct current and AC means alternating current. First of all, we discuss about direct current. The source of direct current is simply a battery. Here we can suppose a battery, and the battery has the positive terminal like this, and there is a negative terminal. And suppose this is a complete circuit. Alright, suppose this battery can flow 1 ampere current. Right. So in direct current, the polarity never changes because the current always flows from positive terminal of a battery to the negative terminal of a battery. This direction preserves. This direction is always constant. So in direct current, the direction does not change. Also, the magnitude does not change because this battery can flow 1 ampere current all the time. There is no fluctuations of this value, we can suppose. If we plot a graph between I versus t, the nature of graph is like this. Here you can see 8 times 0, I is this value, and if time runs, there is no change in the value of current. That means with respect to the time, the value of current remains always constant. Now, next one is varying current. The source of varying current is DC dynamo or DC generator. You can suppose this is a dynamo. This is a dynamo, and the head of the dynamo is connected to the tire of a bicycle. When tire rotates, the head of dynamo also rotates. So rotation of the head of the dynamo depends upon the rotation of the tire of the bicycle. So obviously there might be change in the magnitude of the current developed. The faster is the rotation of the tire, the maximum is the current produced from the dynamo. The lower is the rotation of the tire, the lower is the current produced from the dynamo. That means the magnitude of the current generated from the dynamo always fluctuate, but the direction remains constant. That means if this one is the positive terminal and this one is the negative terminal, the current always flow in this particular directions. That means direction does not change. Direction does not change, but the magnitude changes because the magnitude depends upon the rotation of the tire. So in varying current, the magnitude changes, but direction does not change with the time. I hope you understand. If we plot a graph I versus t for varying current, the nature of graph is like this. Here you can see the magnitude of the current is only in the positive half cycle, but there is no flow of current in the negative half cycle. That is, it is unidirectional flow of current. So from this graph we also observe that the direction is constant but magnitude is varying. So in varying current, magnitude changes but direction does not change with time. And finally, the alternating current. Alternating means the polarity change with time. The source of alternating current is AC generator. In hydroelectric powerhouse, there is AC generator and there is 2 points in the generators, and in this generator its polarity always get changed. Sometimes the one terminal becomes positive, at the instant the another terminal becomes negative, and this terminal reverses. That means positive becomes negative and negative becomes positive. This is due to the cause of rotation of a coil inside the magnetic field. I'm not going to discuss in details about the production of alternating current. In alternating current, magnitude definitely changes, but direction periodically changes. This happens because of, suppose inside the generator there is permanent magnet of N pole and there is permanent magnet of S pole, inside of which suppose there is a coil and this coil always rotates. First time suppose this part of the coil is nearer to the S terminal. In this case, suppose current is flowing in these directions, and during the rotation this part of the coil comes nearer to the N pole, and when this part comes near to the N pole of a magnet, then flow of electric current obviously reverses. This is the practical phenomena, and the direction of flow of current is given by Fleming right-hand rule. So here we see that the direction of current is periodically changes. Also the magnitude changes because during the rotations this coil caught the magnetic lines of force. The amount of current generated from the AC generator depends upon the cutting rate of magnetic lines of force. So in alternating current, magnitude also changes and the direction also changes. So basically we discuss about 3 types of current, but never confuse that the varying current is also a part of direct current. In the first part, magnitude is constant, direction is constant. In the next part, magnitude is not constant, but only the direction is constant. But in alternating current, both magnitude and direction changes. Please pause the video and make a note. Now let's talk about electrical conduction in some materials. Or electrical conduction is due to the drift of electrons in metallic conductor. That means the metallic conductor means you can suppose a copper wire. In the copper wire, the metallic conduction is due to the flow of electrons. And inside the electrolyte means simply like a NaCl solutions. So in that solutions, the conduction is due to the positive and negative ions. Positive ions means Na plus, and negative ions means Cl minus. So like NaCl solution, that means in electrolyte, the electrical conduction is due to the flow of positive and negative ions. And in discharge tube, you can suppose a tube light that we have in our house. Inside the tube light there is a filament and there is a gas, and from the filament some free electrons are ejected, and these electrons can ionize the gas inside the tube and so as to conduct electricity inside of it. So simply in a discharge tube, the electrical conduction is due to the flow of both electrons and ions. Inside the semiconductor simply means a kind of metal. It has a different property. So inside the semiconductor there is a negatively charged carrier, that is electrons, and positively charged carriers, that is holes. So inside the semiconductor the electrical conduction is due to the flow of electrons and holes. Here you should remember that electrons is in actual motions, but holes is always at rest. The motion of holes is defined with respect to the motion of electrons, because electrons can actually move but holes never. Here is a n-type semiconductor. N-type means the semiconductor which have mostly the electrons is called n-type semiconductor. So in n-type semiconductor the electrical conduction is due to mostly the electrons. There might be some conductions due to the flow of positive charge, that is holes, but the motion of the holes inside the n-type semiconductor can be neglected. Inside the p-type semiconductor there is mostly holes, and an electrical conduction inside the p-type semiconductor is due to the motion of mostly hole, that is mostly positive charge. The next one is thermocouple. Thermocouple means that the connection of two dissimilar metals. At the junctions there is temperature dependent potential, and this temperature dependent potentials is calibrated to measure the temperature. So inside the thermocouple electrical conduction is due to the flow of electrons. Finally, the superconductor. Superconductor means a conductor which has almost zero resistance. Suppose helium at 4 degrees centigrade acts like a superconductor. So inside the superconductor the resistance is almost zero. In the superconductor the electrical conduction is supposed to be due to the coherent cloud of electrons. Coherent means same type. The electrical conduction inside the superconductor was determined firstly by the Cooper's the name of the scientist. He found the cause of electrical conduction inside the superconductor, which is due to the coherent cloud of electrons. Alright, so these are the points which are basically important for the entrance. Now let's move on to the mechanism of metallic conduction. Before discussing about the mechanism of metallic conduction, suppose this is the nucleus. Alright, so outside the nucleus there is electronic orbit, and electron moves around the nucleus. In these orbits there are number of electrons that are moving outside the nucleus in a fixed orbit like this. Here we just have to understand the electrostatic force between nucleus and electron. Suppose in the nearest electron, the electrostatic force between nucleus and these electrons might be strong, but as compared to this, the electrostatic force between this electron and nucleus might be weak. So we can easily say that this electron is loosely bound as compared to this. Alright, so there might be some electrons which are actually not attached to the orbit, which we call free electrons. Alright, these free electrons can move in either direction. So in metals, some electrons are loosely bound, that means like this electron, and some are not attached to the orbit of atom, that means like this one. This is the free electrons that we can suppose here. So these free electrons are randomly distributed in all directions, that you can see here. The electrons are moving in all directions, so that there is no net flow of charge in any direction. That means in this conductor, suppose the number of electrons flowing out in these directions is exactly equal to the number of electrons flowing in these directions. So if we calculate the net flow of electrons inside the conductor, we finally get 0. We finally get the value of 0. This means that this part of the electrons cancels this part, so there is no net flow of electrons. So if we consider any cross section of the conductor, the rate at which they pass through it from right to left is the same as the rate at which they pass through it from left to right. Thus net rate of flow of electron is 0. This means that if there is no significant flow of electrons in a particular directions, means there is no current in the conductor. This is the case without the effect of external electric field. You should remember that as we know, the flow of electron consists of electric current. Inside the metal there is atom. Inside the atom there is nucleus, and outside the nucleus there are electrons which are moving, always moving, never at rest. But why there is no current? Because electrons are in motion. But why there is no current? It is simply because the number of electrons moving in these directions exactly equals to the number of electrons moving in this direction. And finally the net flow of electron is 0. This means that there is no flow of charge in a particular direction. That means no current inside the conductor. This is simply a hypothesis. I hope you understand. But what happens when we supply external electric field? When the external electric field is set up in the conductor, the free electrons inside the conductor obviously experience electric force. Because of this electric force, the free electrons moves further with large speed, and during the motion it collides with atom inside the conductor, also rebounds, loses its kinetic energy, sometimes gain its kinetic energy. In overall case, we can say that the motion are not uniform. That is, they are alternatively accelerated and stop. So the resultant motion is significant in a particular direction. That means, suppose this is a conductor, and if we supply electric field to the conductor, there are number of electrons flowing in these directions and some are flowing in these directions, but their motion are not uniform. So finally, if we calculate the net flow of electron inside the conductor through any cross sections, we finally get sum of the electrons flowing in a particular direction. That means if this part cancel out this part, then this part remains. That means some of the electrons are significantly flowing in a particular directions, and so this flow of electrons is responsible for the significantly higher flow of current in this conductor. That means if we supply electric field, the current appears in the metal or in the conductor, but if we not apply electric field, then there is no net flow of electrons. I hope you understand. From these explanations, you have to remember 2 points here. First is, if we do not supply external electric field, actually there is no flow of electric current. But if we supply electric field, external electric field, then there is net flow of charge Alright, so I hope you understand. So here the electrons are supposed to move with an average velocity. We cannot say about the velocity of single electron inside the metal. So it's really difficult, it's really complex. So we finally suppose that the electrons move with a single average velocity at the instant under the influence of electric field, and this average velocity is called drift velocity. Alright, so finally the drift velocity, this is important, it is frequently asked in our NEB board exam. So drift velocity finally means the average velocity with which free electrons get drifted, means shifted towards the positive end of the conductor, because the electron has negative charge and the negatively charged particle always attract towards the positive terminal. And under the influence of external electric field, only under the influence of external electric field electrons get drifted, right? Electrons can move with average velocity. This average velocity is called drift velocity. So one more time, the drift velocity is the average velocity with which free electrons get drifted towards the positive end of the conductor under the influence of an external electric field. Remember this definition, it is very important. Now we have some fundamental concept here, and suppose this is a battery, this is positive terminal, this is the negative terminal, and this is the positive plate because it is connected with the positive terminal of a battery, and this is the negative plate which is connected with the negative terminal of a battery. So here is the flow of electrons that you can see here. The direction of flow of electron is towards the positive plate because it has a negative charge which is attracted toward the positive end. But the electric field is a vector. The direction of electric field is always from positive to negative terminal. So finally we have seen that the direction of flow of electron and the direction of electric field is exactly opposite. The direction of flow of electron and the direction of electric field is exactly opposite. Alright, don't forget. Now finally we have come to the expression for drift velocity. This is important and it is frequently asked in our NEB exams. It carries 4 marks. Now let's discuss about what we have seen first in the figure. So in the figure we have seen that there is a conductor xy. xy is a conductor and small l is the length of the conductor, and here is a battery which has positive, this one is positive and this one is negative. The battery has positive and negative terminals, which is clear in the figure, and the direction of flow of current is always from positive to negative terminal of the battery. So the end of y becomes positive because the end y is connected to the positive terminal of the battery, and this x end is connected to the negative terminal of a battery. So this end is negative and this end is positive. So inside the conductor there is the electric field setup, and the direction of electric field is always from positive to negative end, as we have previously discussed in the previous slide. And the flow of electrons inside the conductor is towards the positive end, because electron has a negative charge which is always attracted toward the positive end of the conductor. Now here is the explanation of the figure. This is my own explanations. You may explain in your own words. So you can write, you can explain about the figure what you have seen here. Simply we can consider a metallic conductor of length L and cross-sectional area A. This is the cross-sectional area A, having electron density N. Electron density means simply number of electrons per unit volume, and which is under the influence of external electric field, such that free electrons moves with a drift velocity Vd. Vd means V and in suffix small d, opposite to the applied electric field E as shown in the figure. This is simply the explanation of the figure. Here total number of free electrons inside the conductor is N. Let N be the total number of electrons inside the conductor, and this number is given by the multiplication of volume and the electron density, because volume means V and electron density means small n, which is capital N by V, and this V cancels out this V, and finally it remains only capital N. This means number. So the number is given by the multiplication of volume and the electron density. The volume is simply given by cross-sectional area A and the length of the conductor, and electron density simply means small n, as you can see here. So number equals number of electron inside the conductor equal to cross-sectional area into length of the conductor. That means volume. Volume means A into L, and the electron density means small n. Alright, since we know that the drift velocity is given by L by T, because suppose this is a conductor and L is the length of the conductor. Suppose this is the electron. This electron comes out through this end in a time t. Then obviously you can define here the drift velocity for the electron as d by t means L by t. Same like this. So from these expressions we can finally calculate the L, and we can put the value of L in the expression. We had n equals volume into density, that means A into L into small n. So value of L is V d t. D is the suffix, don't be confused. So finally we got n equals this expression, right? Now we can find a total charge inside the conductor, which is given by Q equals n times E. E is the charge of single electron, n is the total number of free electrons inside the conductor. So total charge inside the conductor is n times E. So finally this expressions, because the value of n is here, we can put this value of n, and finally we got this expression. And now we can define the current. Current is Q by T. The expression for Q is here, and this one. So this one divided by T, and this T can be cancelled out, and finally we got this expression. So if we rearrange each terms, each parameter, further we get this expression. That means I equals V d E N A. That means V E N A, Vena. Just for easy to remember. So finally the expression for drift velocity is V d equals I by E N A. This is most important. Thanks for watching.